Battery-specific energy hazards differ from those in conventional chemical laboratories. In battery recycling, a waste battery must not be assumed to be safe, because residual energy may still remain in cells, modules, or packs. This can cause short circuits, sparks, local heating, thermal incidents, or fire. Therefore, this lesson focuses on three key controls: de-energization, verification, and no-shorting discipline. In battery recycling, the energy hazard is not limited to electric shock. The main risk is uncontrolled energy release. A battery must be treated as an energy-containing system, even when it is waste or appears discharged. Residual energy can be released suddenly if a metal tool bridges the terminals, or if damage causes an internal short circuit. Damaged separators, crushing, bending, or mechanical deformation can all increase this risk. In modules and packs, one cell event may spread to neighboring cells and develop into thermal runaway. Therefore, always prevent terminal bridging, avoid mechanical damage, and verify de-energization before handling. De-energization means bringing the battery into a safe low-energy state before disassembly. This is not only about electrical safety. If a battery is not de-energized, even a small mistake with a screwdriver, pliers, probe, or metal surface can cause local heating, sparking, or rapid damage. In good laboratory practice, the energy state must be controlled before the battery is opened. This is the starting point of safe battery handling. De-energization and verification are often confused. De-energization is the action. Verification is the confirmation that the action has worked. It is not enough to discharge a battery. You must measure and confirm that it has reached a safe level. In some systems, voltage can recover, measurements can be incorrect, or connection points can be misleading. Therefore, verification is not a formality. It is an independent safety layer. In safe energy control, measurement must follow a clear procedure. First, the expected voltage range of the battery must be known. Then, the correct instrument and probes must be selected, and the measuring device must be checked before use. After the first measurement, controlled discharge is applied, and the voltage is measured again. In some cases, a short waiting period and a second verification may be needed. Finally, the system must be labeled as de-energized and verified. This label is not only information, it is an operational safety message. No-shorting discipline is a fundamental principle of battery safety. Short circuits often result from small oversights, not major mistakes. A ring, a watch, a metal tool, an exposed terminal, a loose screw, or a conductive tray. Therefore, short circuit prevention requires both technical knowledge and safe working habits. Before approaching a battery, the possibility of unintended conductive contact must be systematically eliminated. Disassembly is the stage where energy control is truly tested. In a well-prepared disassembly area, both tools and working behaviors must be standardized. Before starting, energy verification, PPE suitability, and the work surface must be checked. During disassembly, exposed terminals must be insulated immediately, and tools must be used in a controlled way. If any abnormal sign appears, the work must stop. Odor, swelling, sudden heating, or unusual sound are not minor details, they are safety warnings. In this presentation, we discussed why energy control is a central safety issue in battery recycling laboratories. A battery must not be seen only as waste, but as an active system that may still contain energy. Safe practice depends on three main pillars: controlled de-energization, independent verification, and no-shorting discipline. When this logic is understood, later steps such as disassembly, powder control, and chemical processing can be performed much more safely.